Hello everyone. Let us continue the discussion on control unit. We have learned two different ways of designing control units, namely hardwired approach and microprogramming approach. Hardwired approach we have already studied. In the current session, let us learn about microprogramming. In the hardwired approach, we have learned that control logic is considered as a clocked sequential circuit, and therefore conventional sequential circuit designing methods can be used for designing the control unit. We call it as hardwired approach because the final circuit obtained is by physically connecting typical components like gates, flip-flops, and so on. Whereas in the microprogrammed approach, the control functions are simultaneously activated by grouping them to form control words which are stored in a separate memory called as the control memory. The control words are fetched from the control memory, and individual control fields are routed to various functional units present in the data path to enable appropriate gates. When the gates are activated sequentially, the desired task is performed. Retrieval and interpretation of the control words are done similar to the conventional program. The instructions of a processor are held in the main memory. They are fetched and executed in a sequence. By changing the instructions stored in the main memory, the processor can perform different functions. Similarly, by changing the contents of the control memory, the control unit can execute a different control function. Therefore, microprogrammed approach offers greater flexibility than the hardwired approach. Generally, the micro instructions have two important fields, the control field, the next address field. Control field is used to indicate control lines which have to be activated, whereas the next address specify the address of the next micro instruction. The microprogramming approach involves a separate memory called as control memory along with the conventional main memory. Hence, we have to see to that we minimize the length of the micro instruction. The length of the micro instruction is the one which decides the size of the control store and also the cost involved with this approach. Now let us learn about the microprogramming design approach. Consider a simple example. We have four registers A, B, C and D which are connected to a single out bus, and the contents of each of these registers are transferred to the out bus when corresponding control signals C0, C1, C2, C3 are enabled. Since there is a single out bus and four different registers, we cannot have simultaneous activation of these control signals in order to transfer the contents of the registers to the out bus. Say suppose we allocate a single bit to each control in the control field. Then the result will appear as shown in the slide. So when each of the control signal is enabled, we find the corresponding register contents are transferred to the out bus. When none of the control signals are enabled, that is when all control signals are having zeros, no operation is performed. This is called as uncoded format. Now we find that we have 5 different binary patterns in this particular uncoded format. We can just use 3 bits using the switching theory for generating these 5 different binary patterns with the help of a decoder. Consider the diagram shown over here. We have 3 bits as E0, E1, E2 which are the inputs to a 3 to 8 decoder, and out of the 8 decoder outputs, the 5 outputs are used as the 5 binary patterns for enabling the control signals and getting the register contents to the out bus. The relationship between the encoded and actual control information is shown over here. When E0 is 0, no E0, E1, E2 all are 0, no operation is performed. When E0 is 1, register A contents are transferred to out bus. When E1 is 1, register B contents are transferred to out bus. When E0 and E1 both are 1, register C contents are transferred to out bus. And when E2 alone is 1, register D contents are sent to out bus. This is called as encoded format, and this helps us to have short control field and short micro instructions. Now let us learn how to specify the next address of the micro instruction that follows the current instruction which is being executed. In the original design, the next address is specified in each micro instruction. In case of a branch instruction, the address of the next micro instruction to be executed is the address of the memory word that follows the current micro instruction word. Therefore, the next address field from the micro instruction can be eliminated by using a separate register which is used as a pointer to the next instruction to be executed. Since this register is similar to the program counter, we call this as microprogram counter. The microprogram counter is usually incremented after each micro instruction fetch so that it always points to the next micro instruction to be executed. The architecture of a typical microprogrammed control unit is shown in this slide. We have four main blocks: the microprogram counter, the control memory data buffer, and the external condition select multiplexer. As we know, control memory is used for storing the control words. Traditionally, ROM was used. Nowadays, we have programmable ROMs been replaced as control memory. Now let us learn about each of the other three blocks, that is the microprogram counter, the external condition select mux, and the control memory data buffer. The control memory data buffer is also called as control memory buffer register. It is basically a latch and acts as a buffer for micro instructions to be retrieved from the control memory. Typically, every micro instruction will have three distinct fields: the condition select field, the branch address field, and the control function field. The condition select field selects the external condition to be tested. If the selected condition is true, the output of the mux will be 1. Since the output of the mux is connected to the load input of the microprogram counter, as shown in the previous slide, the microprogram counter will be loaded with the address specified in the branch address field of the micro instruction. However, if the selected external condition is false, then the microprogram counter will point to the next micro instruction to be executed. Therefore, the particular arrangement shown in the previous slide allows us for conditional branching. The control in function field of the micro instruction may hold the control information in. The microprogram counter holds the address of the next micro instruction to be executed. Initially, it is loaded from an external source to point to the starting address of the microprogram to be executed. Gradually, the microprogram counter will be incremented after each micro instruction fetch, and the instruction fetched is transferred to the control memory buffer register. Whenever a branch instruction is encountered, we find that the microprogram counter will be loaded with the contents of the branch address field of the micro instruction that is stored in the control memory buffer register. Next is the external condition select mux. This mux selects one of the external conditions according to the contents of the condition select field of the micro instruction. The condition to be selected must therefore be specified in an encoded form. Any encoding leads to a short micro instruction, which implies a small control memory, hence the cost is reduced. Let us consider an example now. Suppose there are 6 external conditions, say x1 to x6, are to be tested. The condition select field and the mux is organized as shown in the figure. So you have a 8:1 mux where the first input is grounded and the last input is VCC, or it is at logic high, and the remaining 6 inputs of the multiplexer is the 6 external condition inputs. The output of the multiplexer is connected to the load or the increment signal or the input of the microprogram counter, and the select inputs of 8:1 multiplexer is connected to the condition select field of the control memory buffer register. So depending upon the select bits, the multiplexer will select the inputs accordingly and give an output to the microprogram counter. So in case of sequential programming, the increment bar signal will be enabled, but if there is a branching which has to take place, the load signal will be enabled. The operation of the mux, the MPC, and the control buffer register is shown in this particular table. Consider a case where the condition field contains 000. The output of the mux is 0. The microprogram counter will be incremented to a point to point the next address. Therefore, no branching will take place. When the condition field bits are 111, the output of the mux is 1. Thereby, the microprogram counter will have to get the branch address. Since this happens regardless of any external condition, an unconditional branch is performed. When the condition select field is 010, the output of the mux is same as the value of the external condition variable x2. Therefore, the microprogram counter will be loaded with a branch address only when x2 is equal to 1. Otherwise, it is incremented. Conditional branching is thereby achieved.